Today, we're diving into the world of three-dimensional motion. Now, you probably feel like you've got a pretty good handle on how things spin and turn, right? But as we're about to see, 3D rotation is, well, it's a lot weirder and way more fascinating than you might think.
Okay, let's jump right in with a simple puzzle. And you can try this right now. Go ahead, grab a book, or even just use your phone. Hold it flat in front of you. Now, rotate it 90 degrees forward so it's tilting away from you. Got it? Okay, now rotate it 90 degrees to the right, kind of like you're turning a key. Just take a mental snapshot of that final position.
All right, now let's reset. Bring it back to flat again. This time, we're going to reverse the order. So first, rotate it 90 degrees to the right, and then rotate it 90 degrees forward. I mean, in our everyday lives, order doesn't usually matter, does it? 2 plus 3 is the same as 3 plus 2. You'd expect to end up in the exact same spot.
But take a look. It's completely different. The final orientation is nowhere near what it was the first time. And this isn't some kind of optical illusion. It reveals a fundamental truth about our universe. When it comes to big rotations in 3D space, the order absolutely matters. They just don't play by the simple rules of addition.
So this right here, this is the core challenge of 3D kinematics. These large, distinct rotations are called finite rotations. And because their order matters so much, we can't just add them together like we do with forces or velocities. This whole problem forced engineers and physicists to come up with a much cleverer way to think about motion.
And the big breakthrough was this. Stop thinking about those big, chunky 90-degree turns. Instead, break down any motion into a series of incredibly tiny, almost instantaneous rotations. We call these infinitesimal rotations. And here's the magic part. For these teeny tiny little steps, the order doesn't matter anymore. They act just like regular vectors, which means we can finally add them up. By breaking a complex tumble into tiny moments, the math suddenly works. It becomes predictable and incredibly powerful.
All right, so now that we've kind of wrapped our heads around the basic problem and the big idea behind the solution, let's actually build a conceptual toolkit that engineers use to describe pretty much any 3D motion you can imagine.
First up, we need a way to describe how something is spinning at any single instant. That's its angular velocity. Now, it's a vector, which sounds technical, but all it really means is it tells you two things at once. The magnitude tells you how fast it's spinning, and the vector's direction points right along the axis it's spinning around at that exact moment. It's like a perfect snapshot of the spin.
But what if that spinning motion is changing? Well, that's where angular acceleration comes in. It describes how that angular velocity vector is changing over time. And this is super important. Because angular velocity has both speed and direction, acceleration can mean the object is spinning up or slowing down, or that its entire axis of rotation is tilting and changing direction. It covers both.
And this is just a brilliant way to picture a really complex idea. As an object wobbles, its axis of rotation is constantly moving. So the path this axis traces from the object's own point of view creates a shape we call the body cone. At the same time, the path it traces out in fixed space generates a space cone. The object's entire wobbling motion, believe it or not, can be visualized as its body cone rolling perfectly along the surface of that space cone. So cool.
Okay, you ready to add another layer of complexity? Because it gets even more interesting. What happens when you try to describe motion not from a fixed, stable viewpoint, but from a perspective that is itself moving and rotating? Think about it like this. Watching a fly buzz around while you're sitting still on a park bench? Pretty easy to track. But now try to describe that same fly's path while you're on a spinning merry-go-round. Yeah, suddenly your own motion makes what you see way more complicated, doesn't it? So how do engineers deal with this mess? They use this incredibly powerful formula, the time derivative equation. This thing is like the mathematical key that lets us translate what we see on that spinning merry-go-round back into the true motion, as seen from the park bench. It lets us account for our own spin to see what's really happening. So here's what that equation is actually telling us, in plain English. The total true change of something is really the sum of two parts. First, there's the change you observe happening right there in front of you from your moving perspective. But then, and this is the key, you have to add the change you don't see, the part that's caused by your entire point of view spinning through space.
Okay, I know we've wrestled with some tough concepts, but this is where we get to the payoff. Let's see how this whole toolkit allows us to precisely describe and even control the complex machinery that's all around us.
Take the mesmerizing motion of a gyroscope. That wobble looks so random, almost magical, but it is anything but. It's actually the predictable sum of three separate angular velocities. There's its main fast spin, there's the slow circular motion called precession,
And then there's that little up and down nodding, which is called nutation. Our toolkit lets us add these all up as vectors to find the total motion at any given second.
And what's really interesting is how these exact same principles apply to something as massive as a construction crane. To know exactly where that bucket is going, engineers have to mathematically combine all the individual motions: the rotation of the crane's base, the changing angle of the boom, the cable getting longer or shorter, and even its swing. It's all just one big, complex vector sum problem.
And this brings us right to the cutting edge. Every precise, fluid, and complex movement of a modern industrial robotic arm is calculated using this exact kinematic language. Whether it's welding a car frame or performing incredibly delicate surgery, it's all governed by the principles of 3D rotation we've been talking about.
So we've gone on quite a journey, haven't we? From a simple puzzle with a book, all the way to some pretty complex equations and real-world machines. But what's the big picture takeaway here? Why does all this stuff matter?
Well, understanding 3D kinematics isn't just some abstract academic exercise. It's literally the language of our modern moving world. It's used in aerospace to guide satellites, in robotics to program those precision movements, and in construction to operate massive cranes safely. It really is the hidden science that makes so much of our advanced technology possible. So, we've just mastered the language of describing motion, which we call kinematics. But that just sets us up perfectly for the next, even bigger question. See, it's one thing to describe how something moves. It's another thing entirely to understand the forces needed to cause that motion. And that, my friends, is a story for another time.